Anybody here know who DataStax is and what DataStax does? All right, one person, 2 people maybe. We're the company behind Apache Cassandra. Who here's heard of Apache Cassandra before? All right, that's better. We gotta get that word association a little bit better. All right. Let's see, I guess. So if you guys in the back can't hear me, then just let me know. But I'll pretend it's working for now. So my job at DataStax is I'm the DSE architect, which means I get to work on Apache Cassandra and things built on top of Apache Cassandra. So I live in a world where relational databases really don't exist, right? I kind of, my first job in the industry was working in a data warehouse. Very much steeped in the tradition of relational databases and schema normalization and denormalization and all the practices within that. And then I went on in my career and I started working on web applications a lot at high scale. And so I ended up taking relational databases in a lot of cases and sharding those relational databases up. Who here's not familiar with the term of sharding? Sounds like something that we all talk about, but the basic concept behind sharding is that we take a big relational database and we break it up into pieces. When we break a relational database up into pieces, we lose some of the properties that give us the nice things that relational databases give us, and all of a sudden, unintentionally, we start working on a distributed system or a distributed database, right? So that's my background, that's where I come from. I made contributions to Apache Cassandra, and as a consequence, I've also made contributions to Apache Thrift and several other projects. Done a lot of work in open source. All of our products at DataStax are based on Apache Cassandra, so we're very committed to open source. I think there are now something on the order of like 11 or 12 committers employed by DataStax, so it's something we do all the time. Now, when we talk about distributed systems, there are several different components that we talk about. One of the most important things that we talk about in distributed systems is availability. Not only do we want to have our data exist, right, but we want to be able to work with it. It needs to be accessible to us, right? And if it's not accessible to us, our database isn't very useful to us, right? Slides, the slides aren't very visible on this projector, but basically I was having a conversation with an engineer out at Twitter who's been involved in the Cassandra community in the past, and we were talking about availability. And it happens that there are a couple of flavors of availability. To me, at the time when I was having this conversation, I thought about availability in one way. Either your application's up or it's down. There's no in between. And if your application's ever down, it's not highly available. And Ryan King, he came back and he said, well, there's another way to look at high availability. There are two major types of high availability. There's MTTR, which is mean time to recovery. And that can be personified, or the metaphor for that could be a United States Army Jeep, right? Has anyone ever seen the YouTube video where you've got a bunch of Canadian Army soldiers driving down the road, and they stop in the middle of a parade, take apart the Jeep, and then put it back together in the course of about 4 minutes? Right? That's kind of the epitome of the mean time to recovery. Right? The engine could go bad on that thing. We could lose an axle. We could lose a major component of the system, and it could be swapped out in a relatively short time, right? And maybe 4 minutes would cause you to lose a race on a quarter mile, but it wouldn't necessarily cause you to lose a race across the country, right? So that's one type of high availability. The other type of high availability that we might look like could be personified, or the metaphor that we could look at would be, say, a Rolls Royce, right? This is called mean time before failure, right? So when you buy a Rolls Royce, if you bring it home and it breaks down in the first week, you're going to be pretty upset. Paid a pretty penny for a car that you would expect to be reliable, that would you wouldn't have to take into the shop all of the time to get small things fixed, right? But when things do go wrong with the Rolls Royce, you probably have to order the part from some factory in Bristol, England, or something like that. You're going to have to wait a while. It's going to be in the shop for a while. You may have to drive your Jeep around for a while until your Rolls Royce gets fixed. availability is a little bit more nuanced than I expected it to be when I started looking at it a little bit more. So, in addition, in engineering, we might look at availability in different ways, or we might look at different systems and we might evaluate them on a scale similar to this, right? So a couple of engineers were having a discussion, and one of them online basically said an analytics system based on Cassandra, for example, where there are no single points of failure might be considered fault tolerant. But if application level data migration, software upgrades, configuration changes take an hour or more downtime to complete, then the system is not highly available, right? So this also reminds me of another story coming out of Twitter where they actually run their statuses, or at least a couple of years ago, they were still running their statuses out of a large MySQL database, right? So all the statuses themselves that come in aren't super huge. I mean, there isn't a lot of data being stored for just people going out and writing statuses on Twitter. Where a lot of that data is in interactions, right? People go out, they look at it, they create things, they comment on it. You know, a lot of the interactions and the graph is actually a lot bigger than the actual data for the status updates. But even the statuses table is big enough that they went in and they said, we want to add a field to the statuses table, right? And what that looks like in SQL is basically to say, go in and alter the table. And when you alter a table in a relational database, generally what happens is that you go through and it will actually change the structure of all the tables. So there's space in those tables for that new field. And when they ran some scenarios over it, they estimated that it would take about 2 weeks to run their alter table statement. It didn't make them feel good at all, right? And they actually balked at making the change in the database and decided to do something different entirely for the feature that they wanted. So availability is complicated. And it doesn't just mean that things fail, but it also means that you may lose some degree of availability in the normal course of operations, in the normal course of business, right? And we've kind of learned to deal with failure at the application level, at least. If you're a web developer, we just had a great talk on web development and databases. But in web development, we've learned a long time ago that websites are brittle and they can fail. They can fail in a lot of ways. They can fail spectacularly. They can fail in minor ways. They can get wedged. All kinds of crazy things can happen to your website. But we've learned that if we spin up enough instances of our website, we have a farm, our single server can fail, and we're okay, right? Because we've got 100 more instances of our website up there, and they'll run just fine. And one user may have had a problem, and as soon as he gets refreshed, he's all right. Why? Because we pushed our state out a little bit further, right? And at first, we might have stuck our state in the middleware, and that might have worked for us. We got sticky sessions and all kinds of other stuff. But then we learned that the middleware can fail too, right? So we made it stateless, and we spin up a bunch of app servers, stick our business logic there, and we didn't care if those failed either, right? Because we could recover pretty easily, right? No problem, right? Child's play. But we're just playing kick the can, right? And we've played this game forever. Kids go out, they play kick the can in the street. Maybe not in suburbia so much, but back, you know, in urban areas, people play kick the can because it's available, right? You take a problem and you make it somebody else's problem. We played this problem forever, either metaphorically or literally throughout the generations. And it's a lot of fun, right? But eventually the fun stops because it becomes your problem, right? So on the database side, again, I was the lead developer on a software as a services platform for a long time. And we built an architecture much like this. Website was stateless. Middleware was stateless. But we ended up, we had a pretty big customer coming online, and we sized our database server, and we said, we think this is big enough, right? So we went out, we bought 2 of them, and we deployed it. It wasn't quite big enough. We did some testing, it wasn't quite big enough. So we went through a couple of iterations of that. We ended up buying this custom hardware. And it was backed by RAM drives and all kinds of other crazy stuff. It was awesome. High performance, it was doing everything we wanted it to do. And we got 2 of them, right? We deployed them out And about 3 days into our run into production, the master failed. We're like, that's cool. We'll just fail over to the secondary. Well, the secondary got corrupted by some data that got messed up by the RAM drives in the primary. And when that happened, our secondary had problems, and so we had to go to backup, right? How long does it take to restore from tape usually, right? Minutes? Hours? Yes. Sometimes days. In this case, it was days. So we were in the airline industry, and you can imagine this airline trying to run their business on spreadsheets until we got the database fixed. It wasn't pretty, and the solution involved lawyers. And it certainly didn't involve a bonus on my part, right, in the end, right? So it was sad. I started looking for other things, right? But we were kind of following best practices. We were doing the best thing we knew how to do at the time. And so when this happened, I sat down with our DBA and I said, look, I think we can do more with the database. And he's like, well, you know, we're kind of pushing it as hard as we can. And it's like, well, what if we looked at this and we didn't run everything at the highest isolation level possible, right? What if we were more fuzzy on our guarantees about consistency? Could it run faster? And he was like, yeah, it could run faster, but everything runs better at the highest level of isolation. And I'm not going to change that. I was like, all right, that works for you. I'm not the DBA, right? But I think we can do more, right? So I talked about this. We can back up to tape. MTTR is hours, possibly days. We can mirror. You may lose data if you mirror. So that's one subtle thing about mirroring. Is if replication isn't 100% and you lose your primary, it's possible for you to lose data when you lose your primary because that data is not guaranteed to have been replicated to your secondary. Which is, if you're not a DBA, which is why your DBA gets really, really nervous when replication gets behind. You might be in your stand-up meeting in the morning, and they're telling you about operations, and they say, replication is 3 hours behind. That means that in that 3-hour window, you may lose data if you haven't replicated that data, if that replication doesn't complete in the primary phase. So you can lose data, right? And that's a sad thing. Nobody wants to lose their data, right? The other problems with geographic distribution of your database, a lot of times if you've got those large replication windows, or replication is taking a long time to get to the secondaries, it's because you've got geographic distribution of your database, right? We have to deal with the speed of light, and TCP is kind of the protocol of choice when it comes to replicating data over large network segments, because we kind of want to know if the data got there, we want to get an ACK back so that we can be sure that they actually received the packets, right? You can create abstractions around other protocols to make it work, but the reality is it becomes sort of a two-phase protocol. So multiple availability zones are difficult because of geographical distribution and the speed of light, right? We would like to break the natural laws like the speed of light, but we're not there yet, right? I don't know. Will we get there? Probably not, right? And this is kind of a natural law that we'll talk about a little bit throughout the conversation. Who here has heard of the cap theorem? We're going to talk about it a little bit. I think there are some misconceptions about the cap theorem. But the idea here is if we end up building a distributed system, and if we want a high availability system, we often are talking about building a distributed system. Because we can't depend on a power company to give us power to a single location in a single place and time, right? If you think about availability zones in EC2, we lose individual availability zones in EC2 every year, right? Some part of US East goes down, some part of US West goes down. They'll lose power to the building. It happens. Either the planned maintenance or somebody with a backhoe messes us up, right? So we would all like this distributed system in which we've got strong consistency, availability, and partitioning, but we can't have them all at once. So for us in the relational database world, in a lot of cases, there's not a great option for having this high availability system. In relational database systems, recovery ends up being a special case because it's a master-slave system. The relational database was really not built with failure as sort of a planned mode, right? Failure is very much a special case. And once you shard it, if you're running a relational database and you've started to shard it, you'll notice that there are certain queries that are difficult to express, right? A canonical example that I like to give about this is eBay, right? There was like a 2006 presentation, eBay said, this is how we build our catalog database, right? And they said, all right, we've got 26 catalog databases. They're on MySQL servers, whatever they were using. I think they were MySQL. Maybe they were Oracle. I don't know. They had one. No, actually, they were a SQL Server shop for a long time. And so they were like, we're going to stick everything in our catalog that starts with A in the first instance, and everything that starts with B in the second instance, and everything that starts with C in the third instance. And now, if you want to do a join between children's toys and toys to see what's similar between those, now you've got a distributed query that you have to write. So what are you doing now? You're reinventing MapReduce. In those days, MapReduce wasn't really a thing outside of Google, but you're writing your own MapReduce style queries to answer those style questions. And they're not even close to real time. They're very much an analytical query that you can use, right? So the problem that we have is traditional databases don't scale horizontally, right? Because information is context sensitive. And when we start sharding that information out, right, that information, that context sensitivity or those relationships become distant from each other, right? And when we change things on one shard, it's difficult to coordinate those changes on other shards. So if we try to guarantee consistency in a system like that, something else has to give, right? And that's kind of the idea behind CAP and the idea behind why, or the reason why people started talking about different things than ACID transactions in the last 6 or 7 years or so. Werner Vogels is the CTO of Amazon, and they're sort of his thing for a long time, or one of the things that he can take pride in is that the Dynamo architecture basically came out of a lot of the needs that Amazon had, right? So Amazon, what's their business? What's Amazon's business? Sell stuff, right? Go online and you buy stuff from them, right? And if their catalog or their ability to sell you stuff is ever not available, they lose more money in a matter of minutes than I make in a year, right? I mean, easily, right? And that's, that's not me bragging. That's just me being wrong, right? I don't even make close to that, right? And if they're down for a few seconds, it impacts their business, right? It impacts their bottom line. And if they're not making revenue, because they don't care about making money, they're losing money all the time, right? If they're not making revenue, then at the end of the quarter, their stockholders are going to say, what happened, right? So they can never be down. So they invented this system called Dynamo. It was a peer-to-peer system, right? And in building this system, they had to think a lot about consistency and how they were going to deal with problems with consistency. He said here, in an ideal world, there would only be one consistency model. But many systems during this time took the approach that it was better to fail the complete system than to break the transparency. And at Amazon, if their recommendations engine fails and they can't sell you stuff, that's a major problem, right? Just because they can't tell you this is what you should buy doesn't mean that they should sell you. They can't sell you stuff. Or just because they're not really sure at this very moment whether they have 3 of these widgets or 0 of these widgets doesn't mean that they're not going to try to sell you one of those widgets. And then after they sell it to you, they're going to say, you know what, we didn't have this in inventory when we tried to stick it in the box and send the box to you. The shelf was empty. So here's $2 or $1 credit, right? Go buy a song on our Amazon service, right? Whether you care or not, right? And we'll ship it to you as soon as we've got it. And if you want a refund, that's fine too, right? So they make these consistency problems actuarial problems, and they actually integrate that into their business, right? So, we alluded to the CAP theorem a couple of times. It was originally posited by Eric Brewer, and they talk about 3 things: consistency, availability, and partition tolerance. Which basically says in a distributed system, we have to make trade-offs, right? With distribution, so we've got these 3 elements, and some people draw this triangle and say you can have 2, right? I don't actually believe that there are 3 things and you can choose 2. I think there are 2 things and you get to make a decision. And I'll talk about that a little bit more. But when you have a distributed database, there's one thing you have to accept, and that's partitioning, right? Network partitions or failures happen in your system. And you can't tell the difference between failed network system from a single place in the network. You can't really tell the difference between a failed external system or a failed network segment. So there could be people on the other side talking to a server that you think is down just because you can't talk to it. Or that server might actually be down, but you don't know because you can't talk to it, right? So there are all kinds of complicated things that happen because of network partitions, and it's something that we have to accept. Networks are unreliable. And if you want strong consistency, any failure of a master will result in a partial outage if we have a master server system or a master slave or I don't know what other words that we use these days to describe those systems, but any system that depends on masters and implies that when you're using a master, you're implying to me, at least from a distributed systems perspective, that you're creating a system where you like some type of strong consistency. And so in the case that we accept that partitioning happens, we have to make a trade-off between availability and consistency, right? And so I work in a world where we mostly use these basically available soft state, eventually consistent systems. And that's kind of the big word for eventual consistency. And one of the systems, one of the things that people always talk about when I start talking about eventual consistency is they say, well, banks can't use asset transactions. And I say, well, banks don't use asset transactions. They do sometimes for some things because now we have the technology, right? We live in the future, right, where we have the technology. But in the past, nobody had the technology, right? Nobody had asset transactions 30 years ago. We certainly didn't have distributed computer systems that even intended to make asset transactions, much less today where they don't really try to do distributed transactions either, right? But if you think about ATM networks, for example, I was in a pretty rural area, remote area, and out on the beach, there was an ATM machine, right? I think it probably had power and maybe had a landline that called back a couple times a day to the central office or something like that. It was certainly in an area where it probably wasn't connected 100% of the time. And there are a lot of edges to the ATM network where the network is very unreliable and it could lose connectivity to the bank. And when it loses connectivity, a lot of times the transactions fall back to a non-real-time state. And I was talking to one of my friends in the financial industry. He said about 80% of ATM transactions are real-time. The rest of them are done offline and in batch. 20% is a pretty big number when you consider how many times ATMs are used or how much ATMs are used today. And so they fall back into this disconnected state where it's sort of an actuarial problem, right? This person used this card matches a hash that I've got saved locally. It says this card is good. I'm going to let them withdraw $200, right? And then I'm going to charge them. I was in downtown Austin the other day and I stuck my card in an ATM machine. It was like a $4 transaction fee. I know right out, but you know, if it's a $5 transaction fee for the risk of, you know, maybe I'm giving somebody, you know, more money than I should out of the account, and this is probably somebody I know, and I can go after them and make more money on overdraft fees if the money's not actually there. I mean, they figured out how to do this and still make money. So in a lot of cases, we can build effective systems even if we don't have complete information all the time. And this goes back, you know, distributed banking goes back a long way, right? And you know, the Templars and the Hospitallars in the Middle Ages were some of the first bankers for pilgrims. You know, where they would sell all of their possessions, and the Knights Templar would say, "All right, here's a voucher. When you get to where you're going, we'll give you all of this stuff back, right? And it won't be the same stuff, but you know, we'll get you started, right?" And so that's in some ways how banks started in Western society. But banks have never been this magical thing where I go up and I magically give you a check, right? And magically I've got money in my pocket at the same time, right? This idea, doesn't really work in the real world. And there's a really interesting article if you're interested, and I don't have a reference here, but go on Google and search for your coffee shop does not use two-phase commit. Really fun article to read that talks about a lot of this stuff. How am I doing on time? Really good. All right. So I talked about partition state fallback. Oh, and banks are special too because all the operations are commutative, right? So I'm adding money to an account, I'm removing money to the account. It doesn't really matter what order those come in, at least for a day's transaction. So I can take those transactions and put time bounds around them, do commutative operations on them. And again, they don't all have to come in order, but as long as I sort of get them all in, then I can order them after the fact. Or, if I don't care about ordering and I only care about ordering over a long period of time, I can order over a shorter period of time and still be okay, because I'm gonna operate on that stuff in batch later, right? And again, a lot of time, risk becomes an actuarial problem in systems like that. All right, so eventual consistency. It means that two queries at the same time could get different results, right? And that seems scary sometimes. And if that's scary for your application, then you might be able to fix it, like Amazon did, like the airlines have, right? Or you could change your business model, right? And this changing your business model, again, another example of a real-world system or a real-world distributed system that predates ACID transactions that sort of dealt with a similar problem, right? I can fit n number of people in a certain configuration of an airplane, right? That doesn't change. I can't put more people on their airplane than there are seats, right? But one butt will fit in one seat, and that's sort of not going to change, right? But if you're my age, you might remember when you were very young, right? If you ever traveled, or your parents ever, called up the travel agent, or maybe there's somebody here that actually called up the travel agent in the past. But in a lot of cases, they did not have connected systems, right? They'd use telex and all kinds of other stuff, to try to figure out if they could sell inventory on an airplane. And the way that they would do it is they basically say, all right, we've got these blocks of seats, and we'll give these blocks of seats away to different travel agencies. These travel agencies are responsible for selling these blocks of seats, and they'll get commission for it, all of that nice stuff, right? And then they'll actually give them tickets. They'll give them, reservations and actually give them tickets, and they'll take these tickets to the airport. At the airport, they'll get seat assignments. And sometimes we'll sell more tickets than there are seats on the plane because of the way that we do this. In that case, we get oversold seats, right? Some of you may have, been bumped from a plane before because the plane was oversold. And that's just sort of an artifact of the way that the airlines decided to run their business back in the day when they couldn't have the guarantees that they could have today, right? In building these systems today, I can say absolutely they don't have to oversell flights. But when they oversell flights, they actually make more money. Because some people don't show up, for one, and they bank on that. And then if all the people do happen to show up, they get into this actuarial mode where they're like, well, we don't want you to be too mad at us, so here's a free voucher, and if you want to take your wife to Hawaii, now you can, right? So they get in a situation where they can actually fix some problems, where they can actually end up running a more efficient business by not assuming that everything is consistent all of the time. And then just sort of let things go a little bit, and then have procedures and policies to fix things when it doesn't quite work out the way that they expected to, the statisticians told them to expect it to, I guess. Right? There we go. All right, so I talked about this. I'm sorry. I don't have like a fancy slideshow presentation here that's telling me what's coming up, so I get a little bit ahead of myself. So we talked all about this, right? All right. There we go. All right. So what if, though, right? What if you're not the airline? What if you're not Amazon, right? You need global distribution, and you need strong consistency, and you need it at scale. I think at 1 o'clock, some of these people that want all this stuff are going to be talking to us, right? Some people want things that they can't have, right? I mean, the horse certainly is not a willing agent in this transaction, right? We all want to have a distributed system that's going to be immediately consistent for everything that we do, and it's going to be fast, and there aren't going to be any trade-offs, but there are no sacrifices or trade-offs that we can make to make this horse uniform, right? The boy can pretend, but he'll never have a real one. And in some ways, we're sad that we're giving up something that we've had for the last 20 years. We've had a really nice abstraction for the last 20 years, 20, 30 years that we've been able to play with, in that we haven't really had to think too much about what happens when data conflicts, when there are data conflicts. But we're sort of running down the road and we're saying, we're getting to the point where we have to decide for ourselves as application developers and as application designers when it's right to make these trade-offs and which trade-offs we need to be making, right? So as a case study, one of the things that I like to talk about is real-time analytics over distributed systems. Because real-time analytics is one of those problems where you've got, let's think, let me use if you're playing buzzword, maybe you might not have been able to mark this off, but now you will. If we talk about the Internet of Things, right? Talking about putting sensors in your toasters, in your refrigerator, in your washer, in your car, everything, right? Sensors everywhere, right? I mean, we were playing around at the DataStax office and we were sticking like scales underneath all the treat baskets, and we could tell every time somebody took one of the treats out of the treat baskets in our kitchen. All kinds of stuff. We put a switch sensor on the refrigerator door, so we could tell every time somebody opened or closed the refrigerator, like all kinds of crazy stuff, because we wanted to collect all kinds of random data about what was going on in our office, so that we could create some pretty cool demos, right? Now, if everybody were doing this, and we were trying to track everybody's activity around the world, which some people want to do, right? I'm not sure why, but we'll find out, right? So people want to do this, right? And as the data comes in, right, if people are doing this activity in China, they don't want to log to a database server in the United States, right? They want to log to somewhere local in China, right? So we're building this distributed system in which we're aggregating a whole bunch of events, right? So if we want to take all of that data, and we want to know, in the last 5 seconds, how many people opened up a refrigerator door in the world, right? Well, as if that will help us answer any of the questions about life and the meaning of things, right? I don't know, but some people want that information. So MapReduce can help us for that, right? Because we can aggregate that, we can run MapReduce jobs, and we can have distributed map jobs, and then bring those reducers in, and then aggregate that data locally. But it's kind of slow, right? And so we built a whole bunch of other systems. Like there's not just MapReduce these days, but we can build systems on top of distributed acyclic graphs like Spark, in which it's not just MapReduce, but we can actually have a pretty rich programming paradigm on top of our distributed systems. They're relatively easy to understand compared to Hadoop, right? How many here have actually messed around with Spark before? Okay, so Spark is a little bit different. Spark and MapReduce are a little bit different from what I'm used to. I work on more real-time distributed systems. These are more in the vein of batch processing, right? You've got a whole bunch of data and you want to run a query on them. And it's okay if you go and get your coffee and you come back and your answer comes back after you've gotten your coffee or whatever cold beverage you might drink in the morning. So with Spark, it's been a project for a while. It's relatively fast, a lot faster than MapReduce, for example. It's somewhat easier to use than MapReduce has been in the past. MapReduce is mostly Java, and I know Java's got a little bit of a bad rap, an undeserved bad rap in the past for being bad for MapReduce. It's getting better. Java 8's brought some primitives that make MapReduce easier. It's becoming a little bit more functional than it has in the past. But Scala and the Python APIs are a little bit easier to use as Spark. It's a lot less code and gives you an interactive shell. Has anybody ever messed around with MapReduce before? Played with the examples? Anybody actually written production code for MapReduce before? It's fun, right? A lot of boilerplate code that you get to write. And if you could read this slide, you could actually see the canonical word count example. I was kind of evil and I didn't remove the import statements at the top just to make it look a little bit worse. But that's sort of how it is. It's a lot of boilerplate code. It's not very natural, right, compared to a functional language, right? If we're going to do that same thing in Scala, you know, here's the Scala shell. Okay, I skipped one line or 2 lines of import there, but basically once you've got that, right, you could go in and you could easily run the same word count demo with, this is a single line, but you know, I'm kind of cheating because it's chained execution here. But MapReduce and functional languages are just a lot easier to deal with, right? So, yes?
Do you think that there's any reason at this point to write MapReduce jobs yourself? With the tools that are out there, like what you're talking about here, Spark,
right.
everything else.
Do I think that there's any reason to write them? Probably. But I don't have a reason to write that in anything but functional languages. I don't know. I mean, if you've already got a built-up infrastructure and you're using a lot of MapReduce already, maybe, right? If Hive isn't fast enough for what you want to do, or Pig isn't fast enough for what you want to do from an optimization perspective. One of the nice things about tools like Spark and Hive and Pig is that when you write your MapReduce job in Java and you say, this is how I'm going to join my data together, that might be a pretty good way to join your data at that time for your understanding, and maybe even for the broader understanding of the community, right? This is what research in the MapReduce community says is the best way to join your data. But in the future, right, they may update the Spark project and Hive's project or Pig project to do joins in a way that is more optimized, right? That reflects new research in the community. And then when that happens, right, you can leverage those innovations for free, right? But you also take the risk of maybe it gets worse for you, right? Because you might be a special flower, right? And so it's always a risk. And so sometimes you may be able to have a short-term gain in doing it yourself, but it's a risk. You can't take the risk out of the equation, I guess is what you're saying. And sometimes it's better for you and your use case to do it in a particular way. So, did I answer your question?
You did.
All right. Now, anybody who has questions, please stop me. Ask questions, right? One of the misconceptions about Spark, and it kind of drives me nuts, is when people are like, yeah, Spark's great, but it's just for in-memory data sets. I think I hit somebody else's pet peeve too. It's not just for in-memory. It's a generalized compute framework similar to MapReduce in that it can work with in-memory better than MapReduce ever really has been able to work with in-memory data sets, not including some of the newer iterations of MapReduce processing like TES, for example. But Spark still has somewhat of an advantage in that it can predefine sets of your data, allow you to cache that data in memory, and then iterate over that data in a way that you couldn't really do previously with only MapReduce style processing. Because it doesn't assume that everything is a mapping and reduce. It's again a general compute framework that uses DAGs. All right. So one of the things that we messed around with a lot of data stacks that we've made free and open for everyone is the Cassandra Spark driver. So you could use this to query Cassandra directly using Spark. Or if you're interested in creating a driver for a different project for Spark, you can use this as sort of a model of how do I get started, or how do I write my own driver for the Spark project. Spark's pretty open, or the Spark project and the Databricks guys are pretty open about wanting to be a Swiss Army knife for data. And one of the reasons why we created a Spark driver for Apache Cassandra was because in the MapReduce world, we always felt like we were second-class citizens because everything was sort of based around HDFS. And because we didn't have HDFS in our ecosystem, really, without creating one of our own, we were always trying to make things work well without having HDFS, which sort of never really worked out very well. With Spark, we don't have to worry about that particular dependency. Everything just kind of works with the Cassandra driver. So all that's great, right? It's nice to have an analytics platform in which we can crunch on a lot of data, but really, one of the reasons why people choose Cassandra in particular
because they need their data in real time, or they need their data for online transaction processing, not for analytics, right? Or not primarily for analytics. So one of the things that I'm going to talk about now is sort of a case study in which we'll talk about real-time aggregation, right? So one of the things about distributed systems that is hard, or that is not really obvious, is that distributed counting is hard, right? So if we're, again, trying to count, how many people or how many refrigerator doors are being opened around the world, and we want that as an incrementing count over time, we could get counts from all over the world, right? And at high volume with geographic distribution, we might want to get sums, or we might want to know something like how many people in China were opening the door, how many people worldwide, how many people in the United States, how many people in Utah, how many people in Provo, right, have been opening their doors, or in that case, have been opening their doors, their refrigerator doors and closing them in the last 5 minutes. How about in the last 5 minutes a week ago, right? This same 5-minute window a week ago. So we want to have aggregations, sums, and counts over periods of time, and perhaps through windows. Let's see, right near real-time counts for increments. Updates can come in non-monotonically, right? So if we weren't talking about, so if we're talking about refrigerator doors, it doesn't matter too much. Things come in out of order. Well, actually, it would matter a lot if things came out of order. So if you had a delay of over a minute and you were trying to get a 1-minute window, if it came in out of order, you kind of need to know when the event happened rather than that the event happened, right? So if they come in out of order, when you do your aggregation or you do your windowing, you can put them back in order and do those increments in the windows where they belong, right? We want to do all of this in sort of real time, right? We don't want to have to wait for our answers as they come in. So can streaming solve this problem for us, right? So a lot of people have been talking about Storm and Spark streaming. And in streaming systems, basically what you do is the data comes in, it gets sent, a lot of times you'll send it into a queue or something like that, and once it's in the queue, you'll send it out to the different systems that you want to do this aggregation. And maybe one of those systems is your database, maybe one of those systems is Storm, maybe one of those systems is Spark, right? But in the case of Storm, for example, the Storm would consume that Kafka queue, and when it's done with that event, it would go back to Storm and say, okay, I'm done. I'm done consuming that, right? And Storm would know, okay, you've consumed that already. I'll mark that done for you. Or no, sorry, Kafka would say, okay, you're done processing that event. I can mark that done for you, right? And that can be helpful, and this can create your real-time aggregates. And again, to do it right, you have to get access from the external system, which in some ways makes it brittle. And there's several things you can do to try to help make it more reliable. But basically, if you don't do it right, and if you're not using queues in front of your system, then the stream has to keep up with your inserts on your database. And it's difficult to even call it real time. Unless you're using Storm, you can get to sort of real time, but Spark streaming does it in micro batches, and so it's only real time in the sense that whatever you set your micro batches to be. And if your real-time processing system doesn't keep up with the rate of data coming in, at least on average over your queue size, then you can back up and your entire system could come crashing down, or you could end up losing data. Either one of those is usually bad. Any questions about this? Right. So streaming can help us in getting the real-time component, right? So we want to aggregate over time, and one way to look at this is if we've got a distributed system, we're probably using some type of replication, probably distributed replication, probably different numbers of replicas across different data centers worldwide. And so a lot of times when you count, you want to count per shard, save the deltas, and then use timestamps to deal with this out of order arrival as it comes in. Yes?
What if the machine has drift?
What?
What if the machine has drift?
Then your timestamps could come from the client rather than the server, because a lot of times the client doesn't have to deal with drift. When an event happens, it spins up a new thread, creates the data and the timestamp for when the event happened. And that's kind of an important point in distributed systems. So a lot of times you don't want your machines that are heavily loaded to be creating timestamps, right? Unless they're generating new threads and a new timestamp on the new thread, which is expensive in and of itself. So a lot of times you treat the edges of your network like the event happened at the refrigerator, right? The event didn't happen when the refrigerator told the database the event happened. The event happened at the refrigerator, so you generate the timestamp there and the data to go along with it, and maybe some other data that goes along with that. Because if you're going to go to Pluto, you might as well bring everything you need with you, right? Go ahead.
Oh, my question was like, what if the refrigerator, since it's been disconnected for so long, has
Right.
to on it?
That's a problem with the edge of your network. So yeah, that could be a problem, right? That could be a problem with your system, and you may or may not want to compensate for that, but that could be a problem. And if you're what I would say is if your refrigerator is connected to the network, put NTP on your refrigerator, right? And if you can't deal with a couple of milliseconds or a couple of microseconds, then you got, and you're dealing with refrigerators, you got other problems, right? Sorry. So yeah, arrival time is important, but the timestamps when the events actually happen are actually important as well. So you have to take all of those things into account, right? So there are probably some things we could, if I'm using Cassandra and I'm trying to create this without any dependencies, right? I could probably create a Cassandra plugin to do aggregation locally. And this is probably a decent design, right? So I could create a trigger inside of Cassandra. When the data comes in, I could pull all of these pieces out that are relevant to the event. And then I could do the aggregation locally in small windows, sort of like micro batching locally in Cassandra, as I also send the data into, say, a big ledger, so I don't lose my actual event as it comes in. So the data comes in, I say, all right, this is data that I can aggregate. The trigger says I can aggregate this, so I send this up to like a singleton. I know that's a bad word, but I send it up to a daemon or a singleton to do that aggregation. And then I store the data locally so I don't lose it, right? So I have the original data, I've got the aggregates, right? But my machine could fit, right? So hopefully after I've written it, it's also been replicated in the system, right? But I may lose, the data in that window, right? So there's a possibility for some failure there. But in the happy case, right, I get the aggregates locally, right, and they're sharded across multiple machines. So I have a piece of the aggregate, and then I have the actual data down stored durably in the database, right? So I can create an API to query for that aggregation because it's not really stored in the database in the same way that the other data is. And then I can create real-time aggregates on the fly. It's because I have all the source data storing it locally. Someone asks me what happened in the last minute or two, I can actually read the source data, or I could actually read the aggregates, right? Depending on how I create the system, I could do the aggregation in real time, or I could do it in batch. It's all up to me, right? And again, of course, you'd want to store that snapshot of data in Cassandra for the windowed aggregation. So that daemon, that singleton that I put up there, every second, every hour, every day, I might snapshot that data into Cassandra so I can read those things individually.
In the case of the refrigerators, wouldn't it just make some sense to have the refrigerator track all the log entries it's sent and then have it just do an authentication with the final destination or destination to call?
So you're saying...
so at the time the door opens, it emits a signal saying, hey, I opened.
Right.
But give it some awareness as to what endpoints are going to be receiving that data, and then have the refrigerator say, hey, by the way, did you get this list of updates that I sent you at these times?
Right, right. So basically having the refrigerator responsible to
validate all
the entries that have come in. That's not a terrible idea, unless that's not a terrible idea. But what are you going to do? The question is, what are you going to do if it gets partitioned and you can't talk to it anymore? Right? It's almost like, well, if we lose a signal, and that might make it more reliable, right? I don't know that I'm too concerned about that in this design, right? In this design, I'm just saying if you get the signal, great. If you didn't get the signal, I'm not too worried about it, right? So because the network is distributed, it's inherently unreliable, and if something's disconnected when an event happens, I'm okay with losing it. Or you could queue it up and send it later, but it would be complicated to have some type of verification protocol between the refrigerator and the remote system. I think that would
if real-time consistency is absolutely paramount, I mean,
right.
if you can't get perfect
right.
real-time, I mean, a redundancy and a consistency where the emitting node is your gatekeeper for its data.
Sure.
Does seem to be quasi-solution.
Right, and you could actually design the system so that in the data that you send to your data store, there could be a unique identifier for that particular thing, right? And then you could go in and you could verify whether or not you received in a digest type format, right? Yeah, you could probably do that verification. I'm not thinking about that right now in this particular design, but that could be an optimization for consistency. One of the things you'd have to deal with though is someone could disconnect their refrigerator for weeks or months, and then you'd have to deal with what happens if I receive month-old data, right? In which case it might be easier just to say I'll ignore it, right? Or at that time you could go in and try to fix up your window aggregation.
But at that point, it's the consumer's responsibility to figure it out.
Sure, could be. Yeah. That's a good point. Yeah, interesting. When we deal with distributed systems in which things can get disconnected like that, things get interesting pretty quickly, right? And it comes down to trade-offs and decisions. So yeah, we can store those deltas as they come in. The aggregates have to be composed of commutative operations, right? Because as the data comes in, if we're running rolling averages or something like that, we have to recalculate everything. So you have to have algorithms that can take data as it's streaming in and add it to whatever you have that's existing, right? Again, cumulative average is a good example of a compatible streaming operation for this type of stuff. And you'll see in distributed systems when they say that they do aggregation, they will really only support operations, at least in the streaming fashion. They'll only support operations that support this type of cumulative or commutative type aggregation, right? So you'll see cumulative average, certain flavors of standard deviation, and other stuff, right? So one place that you can see some of these concepts is in the way that Cassandra does counters. And you can also see some of the hard things and some of the challenges that people have with counters. So distributed counting is hard, but it happens to be a tractable problem as long as you're willing to accept that there are problems in distributed counting that can't really be solved in a fully consistent way. So in some ways, Cassandra already solved this problem. If you look at distributed counters in Cassandra, this is kind of how they look, right? We know when things arrived, right? The window in which they arrived, and we know what the delta is, right? What they're trying to increment to the counter, right? And then the eventual count, right? So we actually have things when they happen, and then there's another concept of shard, right? And then I'll go through this. It'll take a lot of talking. It's easier just to show it this next diagram that I'll come up with here. So nodes can fail. Snapshot of data is stored with a replication factor of 1, similar to RDEs in some cases. So it's possible that you can lose the snapshot of data. But aggregation can be done by a fact client that runs in every node. And if the network partition happens, the real-time component may be inconsistent, but you can always go back to the ledger and you can always recount the data or re-aggregate the data as it exists. And then in case of a node failure, the count needs to be repaired. Right? So in a real scenario, a real-ish scenario, it might look somewhat like this, right? So if we're trying to grab an average, right, and we end up with a network partition in our system, we lose basically visibility to half of our data. It's possible that we may not see some of the partitions on each side. If we don't see some of the partitions on each side and we try to calculate an average, we may come up with a different number on each side of the network partition. And that's bad, right? We don't want that to happen, right? Because we want our counts to be relatively consistent across the system, right? Another way to look at this is that we've got parts of our counts on 2 different nodes if they haven't been replicated to each other yet, right? And so if we want the value for the counter C1, we'll read the value in C1 and we'll read in C1 on shard 1 and the value of C1 on shard 2, and we'll end up adding those together and we get a value of 7 for those, right? And that's the happy case. That's when things go right and we haven't had to do any compensation for that. When we get a partition between those two, again, we can see different counts between those. The way you fix that, right, is these may represent the real-time component, but in the background, there's anti-entropy that should be happening all of the time. And in your real-time or your aggregation system, this may be an analytics process that goes on in the background. In Cassandra, this is sort of all of the anti-entropy processes that are going on in the background, like read repair and offline read repair, online read repair, etc. Right? And in this case, you're taking those shard values and you're replicating them across, right? So shard 1 gets the updates for shard 2, and shard 2 gets the updates for shard 1 replicated across. And in that case, you get all of the values on all of the shards, so that when you read those in the case where you've got a network partition, you see them together and you get the correct count for each one of those values. Yes?
You mentioned banking before, but also banking is being this problem. Could you clarify?
Both problems, right? Banking actually has a real-time and a batch problem, and a batch component, right? So when you go to your online banking application, they say, this is how much money you can withdraw right now. This is how much money we think you can withdraw tomorrow, right? And so they've got a real-time component, and then they're estimating a batch component as well, because they haven't yet reconciled it, right? They haven't said that that money is safe yet to touch, right? And until they run their batch processes at night, they won't say that you can actually have that money. You might be able to walk in, right, and talk to a manager of a bank and get them to give you more money than they say, than the online application says you can, because they know that your check came from a reputable institution, right? But until they actually run those batch processes in the background, they're not going to touch it, right? So in a lot of ways, it's simple. There's a real-time component, and then there's the batch component, right? And once the batch completes, then our historical data will be consistent, right? We won't have to rely on the real-time component. Yes?
Just to underscore that, it is a numbers game. It's been around forever. Arabs had banking, in the 14th century that allowed them to write checks at different ends of the country. Check kiting as a scheme, which is writing a withdrawal in one place and performing this floating cash that prevents reconciliation, is also a scheme that's been around forever. There are opportunities for error, there are opportunities for fraud. And the general consensus, though, is you manage those things statistically. You bring them down to a viable tolerance and then use economics to smooth out what you end up charging people in order to prevent that.
Right.
So we're trying to get the consistency problems smoothed out and smaller, but they've always existed and they've always been exploited. High frequency trading is a great example of trying to do this these days. But it's how do you balance your trade-offs? And that's a real question. So it won't be airtight. It'll be good enough, and good enough is always getting better.
Right. A lot of times it comes down to making a decision, and like you said, taking a risk, right? And in many cases, it actually ends up creating a system that is more viable than a fully consistent system. That's 3 minutes. I'm almost finished. So in our design compromises, our counter increment could fail. The insert could also fail. So we may have under and over counts even in this system, right? So if someone opens a refrigerator door and closes the refrigerator door, and for some reason the network link is broken, right? We may not get that increment, right? Even if they talk to the system and they say, make this increment, and it times out, the increment may actually have happened, but because we didn't get an ACK from the remote system, we don't know whether or not we should send that again, because they may have received it and processed it, or they may have never received the packet, right? We can't tell if that machine has failed, or if the network link failed, or where the network link failed. So you get over and under counts all the time, right? All right. So yes, inconsistency is similar to sharded counters. All of these things may happen. We may fail in mutations. Anything like this may happen. So again, so one of the things that I want to make a point of, I've got a couple minutes here, is that when people talk about the CAP theorem, right? They're not saying you've got 3 things and you need to choose 2. They're saying when a partition happens, you need to decide what your application is going to do as a result, right? Are you going to cancel the operation and say it's not available anymore? Or are you going to proceed with the operation or risk inconsistency, right? And that's a decision you have to make when you design your application. If it's more important that people be able to do whatever they're doing, right? And you can deal with the inconsistent states later, right? Either on the phone or through email or through some background process that happens after the fact, right? then that might be safe for you. If your system being in an inconsistent state is scary and you can't deal with that, or it's impossible to deal with, then maybe you're better off up here in this side, right? But if you need to have a distributed system, it's all about the decisions that you make, right? And a takeaway is when you try to build your distributed system, remember that there's no worse kind of eventual consistency than a broken system that thinks that it's a consistent system. Right. So if you accept it, eventual consistency, realize that your data may be inaccurate, right? Due to network partitions, due to latency, but we can create systems in which historical aggregates at least are reliable, and our real-time estimates are probably close, right? And close within, if we're dealing with pieces of data, close means consistent within a few milliseconds usually, right? So define your failure conditions, make adjustments, set expectations, because failure will happen to you. And if you're building a distributed system, you have to account for those types of failures and what to do. This is a call to action, things that you should learn how to do. Learn a little functional programming if you're not familiar with Scala or Clojure or Erlang or whatever. Just mess around with functional programming because it can help you when you think about distributed systems and the types of things that you can do within a distributed system, like just simple concepts that we think about, like looping, right, become different when you think about them in the context of a functional programming language. Learn about some of the data types in distributed systems like CRDTs. MVCC is really, really important. Try to avoid locking. This is all sort of motherhood and apple pie, but if you're not familiar with some of these concepts, go read some papers that can be really helpful, right? Again, some distributed systems to look at. I like Akka Cluster for people that are just messing around with distributed systems for the first time. Of course, Cassandra is something that I like to look at. I'll post these slides up on the joined in. Sorry, I've gone over for a minute or so, but thank you very much for coming out. I appreciate it.